So on the previous slide, we described the map F from sphere to sphere, and the inverse image of point Y consisted of finite number of points x1 to xm, and we drew a number of conclusions and maps. So let us capture all those maps in the following commutative diagram. Yeah, this is also given on page 136 of Hatcher. So the first map from ui comma ui minus xi to hnv comma v minus y. This map is f star. This is directly induced. It also comes from the number 1 we marked on the previous slide. So that the first map comes from the neighborhood. So second map is also induced from the map F between the two spheres. So this map is also induced by F, and the third map is also induced by F. It is just F goes from Sn to Sn, so it also induces homology maps from Sn to Sn. So the first important point is to understand why these three maps are induced from F. Okay, now we write the excision map. Yeah, so this is the excision map. This was number 2. And this is the map number 3 from previous slide. This came from the long exact sequence. So you understand that these three maps, F star, F star, F star, come from F itself. Yeah, so so the last one from HNV to V minus 5, that is actually number 2, comes from excision. So I will cancel that and rewrite it again. So this is number 3, comes from number 3, which is again long exact sequence. This we will describe later on map J. So we know H and Sn is integers. This is also integers. So since 3 is an iso, we get on the left side integers, then we get integers on the top. Similarly, we try going up on the right side. So yeah, this I told you before is 2, comes from excision. So again we try to travel up, you get integers here and you get integers here. So thus you get a map from Z to Z, and this map, the topmost map F star, is obviously for the point xi. Yeah, so for every point xi you can draw this map. So you can draw this map for x1, x2, x3, x4, x5. So you can keep drawing these commutative diagrams for each xi. And this particular map is now called, obviously it's map between two rings of integers, so it's multiplication by an integer. So this, say it is di, so this will be called local degree of f at xi. So in case f is a homeomorphism, then f inverse of y just consists of a single point, and in that case all the arrows in this commutative diagram become isomorphisms. And we know the homeomorphism, the degree of homeomorphism is plus or minus 1. Okay, now we talk about the proposition 2.30. So which simply says that you just sum up the local degrees at all points. So that is the topmost map. You keep on calculating local degrees di at every point and then you sum them up. So you sum up d1, d2, d3, d4 all the way to dn. So you're just considering the topmost maps. So before I move further, I want to just finish this diagram. I want to draw a map pi, which is nothing but comes from 5 in the previous slide. Okay, so I've marked a star in the left uppermost triangle and I'm going to replicate that triangle here. Yeah, so for a moment consider f inverse y to be x1 and x2 and xi to be x1. So you go back to previous slide and see how we drew the inclusion map pi. Yeah, and we have an accession and this is an inclusion. So basically the isomorphism says that first you go from Sn comma Sn, so via map pi Sn comma Sn minus f inverse yi, or say f inverse of y essentially, not yi, and so you can get to the map hn Sn comma Sn minus xi, but then you can again apply the inclusion map from ui comma ui minus xi to go back. So this to and fro going pi and I essentially means that hn can be expressed as a direct sum. Yeah, so just write this for case x1 and x2 and it will be clear. So it should be direct sum of hn Sn comma Sn minus xi, but instead of that we can write ui comma ui minus xi because we are taking accession. Yeah, again the point is the map pi and I in the triangle on the left side. Yeah, that is what makes the difference. So you know pi is already comes from 5 on the previous diagram and I happens because of the inclusion map ui minus xi naturally goes into Sn comma Sn minus f inverse y, and this inclusion map arises because of the accession. You can go from Sn to ui. So because of this accession, I'm writing now that hn Sn, the generator 1 gets mapped to the direct sum. Yeah, all these. So on the topmost diagram it becomes 1 in the ith dimension. So 1 from the ith dimension, yeah, this is carried over here. So 1 from the ith dimension gets into the centermost part. So this 1 does get mapped to something, yeah. So it's, say it gets mapped to di rather than d1, let us write di here. So for xi 1 gets mapped to di. So for x2, so x1 it will get mapped to d1, x2 will get mapped to d2. So yeah, we are going to write. So on the upper diagram we just showed that where index I gets mapped to, and here we are showing that because of that now we are mapping every I to di. So the way the commutative diagram is all these ones get summed up, and that is precisely our answer, d1 plus d2 to dn. So you should read Hatcher also, which essentially repeats the same argument. So we want to construct a map of any degree k. Yeah, so we will come up with an algorithm which will help us to construct such a map. Yeah, so obviously map f is from Sn to Sn, and this n has to be greater or equal to 1. So we have to consider, other than S0, any n is fine. So how do we do it? So I will draw it for n equals to 2 and k equals to 3, but the procedure is really clear. So you start with the sphere and you take, these k disjoint open balls. Yeah, so in this case let's take 3 balls on the surface of the sphere. So there are this would be k balls. Yeah, so what we do is we collapse the complement of these balls to a single point. Yeah, so complement of these balls, if it is collapsed to a single point, what will we get is a wedge of the spheres, three spheres. So you see the three colors have become three spheres. So suppose this sphere had 3 points. So yeah, so each of these balls have become spheres now. Yeah, it's very clear. So you collapse the complement to a single point, and what you get is a wedge of spheres. Now again, what we do is we further collapse it and we identify all the summits to a single sphere. Yeah, the first map is called say Q and the second map is P. So if there is a point Y here, this Y comes from 3 different points because all these spheres are now identified together. Yeah, and this Y comes from 3 different local points, x1, x2 and x3. So now you can see where we are going. Yeah, so this map is say Q, this map is P. So we are trying to construct for k equals to 3. So you can choose whatever k you want to. Yeah, you just have to choose k disjoint balls. So F is locally it is a homeomorphism. Yeah, so in every neighborhood of the point it is a homeomorphism. As you can see, close to point Y, it gets mapped to x1, x3 and x2. So we want to use proposition 2.30. So the degree of F is equal to at xi, it is plus or minus 1. So now we want to make a choice of say plus 1. If we have to do plus 1, we don't have to do anything, but if we have to take one of the degrees as minus 1, then what we do is we take the corresponding sphere in the wedge sum and reflect it. So if you reflect it, that is nothing but, so you have to reflect it before you compose with P. So a different way of saying it is that you pre-compose with a reflection. So I will write this down. So you reflect one of the spheres whose degree you want to make minus 1. Yeah, so that is pretty much it. So the starting point is you start with the sphere, choose k disjoint open balls, collapse their complement to a point. As a result, you will get a wedge sum of spheres, and with these wedge sums you identify all of them to a single sphere, and then you have a map from Sn to Sn which will be precisely the same map which we drew before.